Hello, pre-calculus students. Hey, welcome to another set of notes. Today we're still talking about limits. Hopefully the previous notes on limits made some sense. You will notice I don't have my graphing calculator handy because we're going to try to do almost every problem today without it. And surprise, surprise, some students are surprised when they take calculus that oftentimes their calculus teacher or professor does not let them use graphing calculators at all. So we need to figure out how to find limits without using a calculator. Now, on the previous notes, I mentioned that there are three different ways to find limits. One is to do it graphically, and we practiced that on the previous notes. One is to use a table of values. We practiced that on the previous notes. And one is to find a limit algebraically. That's what we're going to practice today. So let me explain what I mean by that. So this problem here reads, find the limit as x approaches 2 of x squared plus 2x minus 8 over x minus 2. Now, one thing you'll notice right away, if you plug 2 in place of x, you get 2 squared 4, you get 0 over 2 minus 2, 0. So here's that indeterminate number. We don't know what this is equal to. So just plugging 2 in place of x doesn't help us. Now, you might be tempted at this point to grab a calculator. You might be tempted to look at a table of values. I'm here to tell you that there's another way to do this. And here's what we're going to do. We're going to use our algebra skills. So when you get a problem like this, we want to try to factor what's on top. So I'm going to draw a couple sets of parentheses. And the top can be factored as x minus 2 times x plus 4. And you can double check that by multiplying. But hey, once you do that, you'll notice that, hey, the x minus 2's divide out. They go away. So this whole problem becomes find the limit as x approaches 2 of x plus 4. Now, you could graph that if you want, but you can use what's called direct substitution to just say, hey, if we plug 2 in place of x, 2 plus 4, we get an answer of 6. And if you want to verify that on your calculator by graphing the original function, tracing it, looking at a table of values, you will see that as x gets closer and closer to 2, the value of y gets closer and closer to 6. Now, for this original function, when x equals 2, y doesn't exist because remember it's 0 over 0, but the y value will get closer and closer to 6. So if you can simplify this expression algebraically, there's no need to use a calculator. There's no need to graph and trace. There's no need to look at a table because we can plug the 2 in eventually and we'll get our answer. Oh, that's kind of cool. All right, let's look at another example. Okay, there's one like this in our notes previously as well. So we're finding the limit as x approaches 2 of this function. And just so you know, if you plug 2 in the top, you'll get 0. If you plug 2 in the bottom, I won't bore you with that calculation, but you'll also get 0. So making that substitution right away doesn't help us at all. But let's see if we can simplify what we have. Now, you might look at this and say, what? We have to factor what's on bottom, but here's something we know. We know when we plug 2 in there, we get 0, which means 2 is a 0. And we can divide x minus 2 out of there using synthetic division. You might say, whoa, we haven't done this in a long time. And imagine that. Something we did first semester is coming up again, and something that you're gonna see this next year in calculus. All right, let's remind ourselves how this works. We add down, we multiply diagonally. Add down, multiply diagonally, add down, multiply diagonally, and add down. Now, getting a 0, there's a good sign. It means it divided out evenly. So here's what that tells us. Well, the top is still x minus 2. We haven't changed a thing. The bottom is going to be x minus 2. That comes from this part out here. Times, from this part, 1x squared plus 2. All right, now, at this point, we can do some simplification. So what we're left with is the limit as x approaches 2 of 1 over x squared plus 2. And at this point, now we can use direct substitution and plug that 2 right here for x. Well, that's going to give us 1 over 2 squared is 4 plus 2. That's going to give us 1/6. So if you would have graphed this to start with and traced it and saw as x got closer to 2, the value of y would get closer to 1/6. Now, ladies and gentlemen, this method is better than graphing and better than using a table of values, and here's why. Graphing, you would see like, oh, you get an answer like 0.16 or something. Table of values would give you like 0.17. Algebraically, this gives us an exact answer that we probably would not get if we just graphed or used a table of values. So finding limits algebraically is actually the best method to use if we can. There are certain times when we can't because there's no algebra we can do, but a big part of calculus is learning more advanced algebraic strategies so that you can always simplify something like this. All right, so you actually could look at most of the problems you did on the previous set of notes and do them algebraically. All right, let's step it up a little bit. Let's take a look at a more complicated problem. All right, here we go. Take a second to jot this down. We're finding the limit as x approaches 0 of the square root of x plus 9 minus 3 all over x. Now, just one nice thing to check right away. Let's plug 0 in and see if we get anything. On top, 0 plus 9 is 9. Square, that's 3 minus 3. And at bottom, we just get 0. So doing that direct substitution right off the bat led us nowhere. Okay, that didn't help us at all. All right, we can't really factor, we can't do what we did in the previous problems. There's a trick to a problem like this, and you see these kind of problems a lot in calculus. All right, here's the trick. Back in your geometry days, back when you were in geometry, you learned that when you had a problem, now you don't have to write this down, but if you had a problem like this, like 3 over the square root of 2, your geometry teacher probably said, we can never leave square roots in the denominator, so let's multiply top and bottom by the square root of 2, which is going to rationalize the denominator. That'll give us just 2, and there's an equivalent answer. Now, here's the deal. In calculus, a lot of times the square root in the denominator is okay. In fact, on this particular problem here, this problem is impossible with the square root on top. But if you had a square root on the bottom, it would be very possible. So what we want to do here is what's called rationalize the numerator. We want to get the square root out of the top of the fraction. And here's how we do it. We're going to multiply top and bottom here by what's called the conjugate. Oh, we've heard that word before. We're going to multiply top and bottom by the conjugate of what's on top. So when you see these problems, that's just a trick we need to know. It's a strategy we need. We need to know that we can multiply the top and bottom by the conjugate of what's on top. And here's why we do it. Because if you multiply what's on top, square root of x plus 9 times square root of x plus 9 is just x plus 9. Now watch what happens here. Square root of x plus 9 times 3 and square root of x plus 9 times negative 3 are going to add to 0. I'm not even going to write those down. And then negative 3 times 3 is going to give us minus 9. Hey, that's cool. Now, you might be tempted to distribute what's on bottom, but I'm here to tell you, do not distribute. You'll see why in just a sec. Okay, see anything cool on top? Well, you should. Plus 9 minus 9, that adds to 0, that goes away. Now, do you see anything cool on top and bottom? Ooh, there's an x on top and x on the bottom. Those divide out. That leaves you with 1 on top over what's on bottom. So here's what your problem becomes. The limit as x approaches 0 of 1 over the square root of x plus 9 plus 3. This fraction is equivalent to what we started with. It's a different way of writing it. If we write it this way, now we can do direct substitution. We can plug 0 in place of that x. And here's what that gives us. It gives us 1 on top over, ooh, that's kind of weird. 0 plus 9 is 9. Square root of 9 is 3 plus 3. And if we do that, we get an answer of 1/6. So here's the deal. If we were to graph this to start with, if we were to look at a table of values, as x got closer and closer to 0, the value of y would get closer and closer to 1/6. Algebraically, we know that it becomes almost exactly 1/6. As x approaches 0, it gets infinitely close to 1/6. So, just to review, this is a tough one. If we have that square root on top or on bottom and we need to simplify, we can rationalize, in this case, rationalize the numerator. The square root on top is going to go away. It's going to give us an expression that we can directly substitute into and come up with an answer. All right, hopefully that makes sense to you. And there was a problem in our notes previously that we could go back and do using this method, but now we can use this method moving forward. Okay, let's shift gears a little bit. So the first three examples, that's really the gist of what you need to know for our notes today, okay? I'm going to go through this fourth one here is more of a notation problem. I want to show you what something means that you've never seen before. The fifth one is a piecewise function. We'll see that. And then there's 1/6 example that's going to lead into tomorrow's work. Okay, so the problem says find each of the following. Now, there's something different you've never seen before in these problems. And it's this sign right here and this sign right here. Now, you might say -0, +0. What's all that mean? Here's what it means. Here's how you'd read this. You'd say, find the limit as x approaches 0 from the left. That's what that means, of this function. This means find the limit as x approaches 0 from the right of this function. Okay? Now, instead of doing this algebraically, I am going to grab my calculator here. So let me get that out here. Let's see if we can graph this one. There you go. Sorry about that. Sorry about that smudge. I'll get rid of that. Should be gone. Okay. And I'm going to press my y equals key. I actually typed it in ahead of time. I knew it'd be coming up to this. And if I graph that function, I can see that it looks like a horizontal line, just barely traces this axis, and then same thing on top, but there seems to be, you know, a little bit of a jump in here. If I trace this function from the left, as x gets closer to 0, y equals -0.25. From the right, as x gets closer to 0, y equals +0.25. And I'm just going to take a look at a table. I'm going to start my table at 0. And I notice when x equals 0 itself, there's an error because we'd have 0 over 0. But from the one side, we get -0.25. From the other side, we get +0.25. When we saw one of these the other day, we said DNE. We said the limit does not exist. But if we're just saying when x approaches 0 from the left, and thinking about our graph, when x approaches 0 from the left, the value of y was -0.25 or -1/4. When x approached 0 from the right, the value of y was +1/4. Now, these answers are legitimate. This is okay. We don't have to say it does not exist because when we see this notation, it means we're only looking from the left-hand side. And this is what the answer was. When we see this, we're only looking from the right-hand side. This is what that answer was. Okay? So when you see that notation, and we won't see it a lot in this class, but you will see that next year in calculus. Just know that means we're only tracing our graph from the left and from the right. Okay, I'm going to put my calculator aside once again. Let's go to our second to last example, and it's a piecewise function. So the problem says, find the limit as x approaches 2 of the function, where, and here's your function. Okay, now I'm just going to make a rough sketch of this graph. And if you're looking at that and thinking, I don't know how to make a rough sketch of that graph, don't worry. I'm going to show you a shortcut. Because remember, our goal today was to figure out how to find limits without using a calculator, without graphing, without tracing. Okay? So here's what this is saying. It's saying y equals x squared plus 1. So our function is x squared plus 1 for x values less than 2. Well, that's a parabola. So that first part of the function looks something like this, but then stops here. The second part of the function, y equals negative 1/2 x plus 6, that's a line. Slope of negative 1/2, y-intercept of 6. If we graph that, you get something that looks like this. So there's our two pieces of the function. Now, if we were doing this graphically, we'd trace the left-hand side, we would trace the right-hand side, we'd see what value does this approach. I'm going to show you a shortcut method that we can use algebraically so we don't ever have to make these graphs again. Check this out. Here's what we can do. We can say, let's take this number 2 and let's plug it into each of these functions. Okay? Now, if we plug it in there and we get the same value, that means that these graphs are approaching the same y value, and that's our answer. If we plug it in there and we get two different values, it means that these graphs are approaching two different numbers, and maybe these graphs were there, so maybe they look something like this or like this, and they don't meet. Okay? So let's plug 2 in there and see what we get. So if we plug 2 into this top part of the function, we get 2 squared, 4, plus 1. We get a value of 5. If we plug 2 into the bottom part, we get negative 1/2 of 2 is negative 1 plus 6. We also get 5. That means that's our answer, ladies and gentlemen. No further work required. So the nice thing is with these piecewise functions, if you plug the 2 in the top and bottom and get the same thing, that's your answer. Now, if you plug the 2 in top and bottom and get different things, that means these graphs don't meet. That means we would write DNE, the limit does not exist. Now in this case, they do meet. In this case, you get the same value, so that number is our answer, and we're totally done. That's all the work we have to do. Okay, people, so our goal today, we saw how to find limits algebraically. We saw a notation, like what's it mean to get a limit from the left and the right. We saw how to do a piecewise function algebraically, which is a heck of a lot easier than what we did yesterday. And I saved one last problem for you. Now, this last problem here, this is calculus, ladies and gentlemen. If you've always wondered what calculus is, this is going to give us a preview of tomorrow's work. And this, my friends, is the most important formula you'll see in calculus. You'll see this right away. You show this to any of your friends in calculus, they know exactly what this is. We'll get more details tomorrow, but I want to give you a preview of this. So this is saying we want to find the limit as h approaches 0 of this function. Now, if we plug 0 in the top, we'll get f of x minus f of x. We'll get 0 over 0. So what we have to do instead is we have to simplify this by using this function we have. Okay? Let me show you what I mean by this. So this first part says find f of x plus h. That means we want to write f of x. We want to write this function, but put x plus h right there. Okay? So let's do that. So I'm going to write the limit as h approaches 0 of, and I'm going to write this entire function, but put x plus h right here. So I'm going to write 2 times x plus h squared plus 1. Now, next thing I have to do, this says minus f of x. That means I'm going to subtract all of f of x. And hint for you, put it all in parentheses. So minus 2x squared plus 1. And then don't forget what's on bottom there. It's all over h. Okay, so just a review of what we did. F of x plus h means put x plus h right here in place of x. That's this in blue. Minus f of x means subtract the entire function. That's here in green. Make sure you always put it over h. Okay. Now, let's simplify things. So, first thing to simplify, we have x plus h squared. I'm just going to write that up here to remind myself that x plus h squared means x plus h times x plus h. Okay, so if I multiply that out, I've got 2 times x squared plus 2xh plus h squared. That's this part, plus 1. And then let's distribute this minus while we're at it. Minus 2x squared minus 1 all over h. And don't forget we've got a limit in front, so the limit as h approaches 0. Okay, let's give ourselves some room to work. Okay, let's simplify some more. I've got this 2 in front of these parentheses. So I'm going to distribute all of that. Let's see what we get. That gives me 2x squared plus 4xh plus 2h squared plus 1 minus 2x squared minus 1. Wow, what is going on? And then all over h. And still that limit in front. Okay. Now we've got a little more algebra we can do here. Check this out though. See this 2x squared? See this minus 2x squared? Gone. That adds to 0. See this 1? See this minus 1? Gone. That adds to 0. So here's what we have left. We've got this limit as h approaches 0 of, on top we have 4xh plus 2h squared all over h. Wow. Now check it out. Every term on top has an h. We could factor that h out, and if we did factor it out, it would divide out with the h on bottom. So one of these h's here, one of these h's here, and this h are all going to divide out. So we're left with, let's give ourselves a little more room here. Here's what we've got. The limit as h approaches 0 of, that h is gone, so I've got 4x. Here we have plus 2h. At this point, we can do direct substitution, plug 0 in place of h. This would be gone totally. Here's our answer. Our answer is going to be 4x. And it's perfectly okay if you get an expression for an answer for this kind of problem. In fact, most times you will not get a number answer. You'll get an expression. Now, that's a lot of work. Let me scroll back up here. So when we have these limit problems, man, what is that? Sorry about the technical difficulties. So the toughest part was the beginning, the first step. I apologize for that. I don't know what's going on with that. Once we do that first step, we do our algebra, and we come up with this answer, which is an expression. Okay, ladies and gentlemen, hopefully this makes sense. If not, be in contact with us. Let us know what's going on. See what you can do, and there's more good stuff to come. So check out the next couple videos in the next couple days. All right, take care, everybody.